Hello guys, today we're going to be covering section 2.2, which is going to be the limit of a function. So limits are kind of like a weird thing to think about at first and take a while to get used to. So it's always like nice to see them in like a more natural setting first. It's kind of like, let's try, I don't know, let's try working with an example and just kind of see what happens. So let's consider a function f of x, which is equal to x squared minus x plus 2. I want to see what is behavior of f. If I can spell behavior right. F of x when x is near 2. So what that means is, like, if we look at the graph, which I'm going to sketch out right now, like, what is the function doing whenever x is, like 1.9, 1.99, or, like 2.1, 2.001, for values that are, like, close to 2. So bear with me, I'm not the greatest artist, but we'll figure it out. I should go like this. So this will be 2 right here. And let's go ahead and just draw like a little plot right here. So now we're gonna get, we're gonna plug in values that are pretty close to 2. That way we can get an idea like what is the behavior of f of x near 2. So here it'll be like 1.9, 1.99, 1.999. We do 2, put a little question mark because that's kind of what we wanted to know. And then like 2.001, 2.01, and 2.1. So maybe it's not so obvious depending on my, crappy drawing. But, like what we can see here is that as we get close to 2, the function actually gets closer and closer to this point right here, which is actually 4. And we can see that when we actually plug in like numerical values. So whenever we plug in different x values, we get, values that actually make sense with the graph. So for 1.9, we get 3.71. For 1.99, we get 3.97. And 1.999, we get 3.997. I'm just going to go ahead and fill out the rest. So 4.003, 4.03, and this is like 4.31. So what we see is as we get closer and closer to 2, we, from the bottom, 1.9, 1.99, and as these numbers get closer to 2, we get this number right here. I think it's easy for you guys to see, including on the graph, you see it. It's closer to 4. And then if we, it's not there. And as we see, as this gets closer and closer to 2 from above, and we say above to mean like, the numbers that are greater than that, we get numbers that also go to 4. So this kind of gives us the idea that, the behavior of fx when x is near 2 is that it approaches 2. Well, not approaches 2, but whenever x approaches 2, f of x approaches 4. And it's kind of the main idea of limits. Because it's kind of curious, we're curious to see what happens to functions whenever we approach certain values. Like, does the function go to infinity? Does it, have multiple limits? But the idea is, what's really going on is, we can make, let me just write it out first. We can make f of x as close to 4 by taking x to be as sufficiently close to 2. So this means is that if we want, if we want the values of f of x to be, within like a certain radius, or let's just say we only want them to be cracked up to like 10 decimal places, well, we have to put the restriction on f of x first, and that will appear as another restriction on x. So basically it just means that your x's depend on your f of x. So you can't just choose your f of x. You can't technically choose these first, your x's first, to do that, to say, like f of x is always near 4, but, that's just a bit of a technicality. But anyways, like, what does this mean? Like, how can we say that? So the way we actually say it would be, like, the way we would say it with words is, we say that the limit of this function, f of x, as x approaches 2, is 4. So what this means is, what this is saying is that as we go to 2 from above or below, again either from numbers less than it or numbers greater than it, then we have that f of x goes to 4. And we have some notation for that, because, obviously you have notation for everything. So the notation the way we would say that would be the limit as x goes to 2 of f of x is equal to 4. In this case, f of x is equal to a specific function, so what we would actually write would be as limit as x goes to 2 of x squared minus x is x squared minus x plus 2. And that's how we'd write that. So again, this part here kind of clarifies what values of x we're taking. And and this is kind of telling us what the function is doing. So what we're saying right here is, as x goes to 2, this function right here goes to 4. So let's kind of, make it more arbitrary. Let's try to generalize a bit. Because here I'm talking about a specific example. What happens if we just say, an arbitrary function, and we choose an arbitrary, thing to approach. So this will be like a definition. I use that shorthand just to say definition. I don't know why at the end, but that's usually how I do whenever I just write definition. Alright, so we say, suppose f of x is defined when x is near a. We shall note, but not necessarily equal to a, so it doesn't mean that the function has to be defined there. Then what we write will be like, the limit as x goes to a of f of x is equal to L, and so we write that whenever a function is like defined near x of a, defined near a, and the if comes from this kind of statement again, that this values of, f of x as close as we made them before, we can do that as we take x sufficiently close to 2. So now we're just going to generalize that. So we take the limit of f of x as x goes to a is equal to L if we can make f of x as close to L, and as close to L just means we can make it as close as we want. We make it arbitrary close, it doesn't matter, but we can choose that. We can choose it. and then f of x is close to L, and then because of the fact we're choosing, we have to do that by taking x to be sufficiently close to 2. Well, not 2. Oops, my bad. Close to A. And again, we say but not equal to A. And the reason why you specify not equal to A is because the idea behind limits is they're about local behavior. They're not actually about what you're doing. You're wondering what everything around you is. So you don't necessarily have to be defined at your limit. You don't have to. You can be defined at your limit, and if you are defined at your limit, then you don't have to be there. And you'll see what I mean in just a second. So there's 3 kind of examples where we have, like a common limit, but 3 different situations. All right. So I'm gonna try to draw the same function. Well, obviously not the same function, but something that looks very similar. Crap. So let's just take this example. So let's call this x, call this y, and let's take a function that just looks like this. And bear with me since it's hard to erase. Let's just say there's a hole right here. Oh no, we're not starting with the hole. That would be weird. So let's consider this. Fuck you damn iPad. Alright. So let's call this point 1. Let's call it, 2. And then we say that's going to be, and that curve defined by that is just going to be f of x. So this makes this point right here f of 1. So it's easy to see here, kind of based on what we did earlier, as, x approached 2, then we had the function approach actually a certain value, in this case which was 4. So we're going to do the same thing here. We say as x approaches 1, the function is going to also approach 2. And then as we approach 1 from the other side, the function also is going to approach 2. And the fact is that, remember, limits actually, the thing with limits is that we have to approach them from both sides. If we approach them from, 2 different sides, we get 2 different values, then that's actually, we say the limit does not exist. But I'll get there in a second. So the fact that they equal to one value, the same value, means we can say the limit as x goes to 1 of f of x is equal to 2. In this case, f of 1 is equal to 2. But that's not always the case. There's a few other cases that can happen, but do not change the limit. That's why. Let's see if I can. Oh, that's close enough. Nah, I don't like it. All right, that's close enough. Pretend it's the same curve roughly. So here will be 1, and call this point 2. Now we're just going to put a hole there. So now we say, f of 1 is not defined. In this case, we still want to know, what is the behavior as we approach 1? Because, f of 0.9 is okay, f of 0.99 is okay, f of 0.999, 9, and we can keep on doing that. But we just can't plug in 1. But we can get really close to 1. We can get as arbitrarily close to 1 as we like. So that's kind of then the question is, again, what is happening to f as we approach 1? And then we can still do the same thing. So if we approach 1 in the x values from the left, then what's going to happen is the function is still going to be approaching this value 2. If we approach it from the right, then as we follow down the function, it's also going to be approaching 2. It's never going to get there, but it's still approaching 2. So in the same case, we still say the limit as x goes to 1 of f of x is equal to 2, but f of 1, we'll say, does not exist. Or in this case, it's just not in the domain. So the fact is that you don't need to be defined at, the limit point doesn't necessarily have to be in your domain, but you can still be defined there. You can still have a limit there. And even if you are defined there, you don't actually have to equal that value. So say this is 1, this would be 2. And then now let's put a hole right here, if I can make that a hole. Not what I wanted. Alright, so now let's make a hole here. And now what we're doing in this example, this is still f of x, but we're going to put this point right here, we're going to say f of x is equal to 1 there. So in this case, now we still want to do the limit. So let's approach 1, and as we approach 1, the function is still approaching 2. And now if we approach 1 from this side, this function is still approaching 2. So in this case, the fact is that if we come from 1 from the left or from the right, we still approach the same value. So then we can still say the same thing as we said in the previous problems. The limit as x goes to 1 of f of x is equal to 2. But in this case, f of 1, I don't know if I made it clear enough, is actually equal to 1. So in this case, you don't have to, in this case, when you approach a value, you don't necessarily have to be there specifically, the function can have a limit, but the function at that point doesn't have to equal the limit. In this case, we're going to learn about this later on, but we would say this function is not continuous. And the fact is, and in this case right here, and in this case right here, we can still have a limit even though we're not defined there. And again, what that means is we just have a hole. And that's what this specific setting is just called. That would just be a hole. And in this case, we can have it where the limit exists and we are defined there. And a function that satisfies that property, we would say is continuous. But again, we're not worrying so much about that right now. So one of the things is how do we find these limits? If we look at the graphs, it's kind of clear, but sometimes the graphs might not be helpful. Or one of the other things we did, when we first started this, we did these numerical charts. And, we just plugged in different values that are close to x. But the thing is choosing values like that, just willy-nilly, even if you choose a specific, x values near a certain number, they're not always good. So I'm just going to make a claim real quick. Or not make a claim, but I'll say numerical charts aren't always good for investigating limits. Or not always. I can spell always. Oh, that's the word. Accurate. My bad. I need to look at my notes when I actually write this. Alright, so I can't just say something without, proving myself or, kind of proving why this is true. So I'm going to give you an example of an example of a specific function where you can create a sequence that goes to basically anything you want. So let's start off with, again, come up with a specific counterexample of why sometimes just guessing numbers like that doesn't work. So let's consider a function, say, let's try to evaluate and we're going to do the limit as x goes to 0 of sine of pi divided by x. I'm going to figure out what happens to that as x goes to 0. So let's try, let's try to do a numerical chart. here we're going to do, this will be f of x, or, sine of pi x actually. So now if we plug in 1, we just get the sine of pi is equal to 0. If we plug in 1/2, we get sine of 2 pi, which equals to 0. Because we divide by half, that half becomes, like multiplied by the reciprocal, so you just get 2. Well, 2 pi. So if we do, like 1/5, we get sine of 5 pi, which is equal to 0. If we do like, 1/100, we get sine of 100 pi, which is equal to 0. And we can keep on choosing numbers like that. Any number that's like of this, of just 1 over, some integer, is actually going to be equal to 0. So what this suggests is that, based on how we did the problem earlier, that the limit as x goes to 0 of sine of pi over x is equal to 0. But that's not true. And we're going to see why it's not true whenever we do the graph. So I'm going to try to draw the graph. Bear with me, it's a very funky looking giraffe. It's a very funky kind of graph. So I'm going to do my best to sketch it. 1. So I'm going to put something here. But basically what's going to be going on with this function is that, sine of x likes to oscillate. And as x goes to 0, the pi over x term begins to grow unbounded. And as it grows unbounded, that basically makes the frequency of the limit of sine of x, or like the sine pi of x as it gets close to 0, go to like infinity. So what this looks like is, let's see if I can draw this right. Okay, so this should be like, it's going to be coming down through 1, it's going to hit 1, it's going to bounce up. And then as we get closer and closer to 0, the distance between the peaks is basically going to get closer and closer to 0 as well. And basically, like, at this point, and the thing is, like, what we're doing with these numerical values right here, is that these points right here, what they do is they match up with these points right here. And so the limit of these sequences, again, of this specific sequence is equal to 0, but it's not the one of f of x. Because one of the things we could do is just, not what I wanted. Is instead of choosing like, the zeros, we could choose the peaks. So, these right here are going to be like, let's see, I think 2/3, I think, like 2/5, and so on. That way we could just get, pi over 2. So we just get like 1, 1, 1. So you just make a sequence of 1s. So that kind of tells us that we need like, better ways or like, more precise methods to calculate limits. All right, so there's another way that we can do, there's another way we can do limits, but kind of specifies the direction. As you notice when I was like doing these, I was saying, from the left or from the right. So we can actually take those limits separately. Instead of taking them at the same time with just a standard limit like this, we can choose the direction which we're doing. So these functions, or not these functions, but these limits, they're called one-sided limits. And sometimes limits may not exist, and if limits don't exist, it's probably because of the left and right limits. So first, let's consider a counterexample, or like, kind of function where we would actually like, think about this. Or, a function where we might want to actually think about one-sided limits. So consider the function In this case, the function is going to be h of x. It's actually called a heave side function and has, specific applications in engineering. I think specifically like signal process or something like that, or electrical engineering. But it's going to be 1 whenever x is greater than or equal to 0, and going to be 0 for x less than 0. So what this looks like is alright, so this will be 1, and we can say, let's call that the y value, the h of x, and we call this x. Alright, so as h of x is going to be 0 for all values less than 0, that means what this function is doing is just going to be approaching 0, and then going to be a little hole right there. And then it says it's going to be 1 for whenever x is greater than or equal to 0. So it's going to be 1 here, it's going to be filled in circle, and then it's going to stay at 1. So, and this idea is that the limit right here is not going to exist. So in this case, the limit as x goes to 0 of h of x, I don't know if I said 1 earlier, but whatever. Limit of h of x as x goes to 0, it actually does not exist. All right. And the reason for that is because, let's look at the, what kind of happens as the function actually approaches 0. So if we approach 0 from here, we have, the left-hand side actually approaches 0. So actually, let me write that down, because the way we write that is actually very specific. So when we approach 0 from the left, we have that h of x approaches 0. And from the left just means we're choosing, and we have to kind of specify what the left means. Let me just actually clarify. So left means values, or we say we say x is less than 0. That's what that means. We choose something that is less than the limit. And then we say, looks like I'm changing colors again. All right. When we approach, 0 from the right, we actually get 1. And again, so kind of like the left, we were approaching from values that were less than 0. In this case, we're approaching values. We say the right, we mean we're choosing x values that are going to be greater than 0. That's why the way we would typically write it, I would just immediately jumped up there, but okay. The way we would write that would just be as, 0 is less than x. That way, here is x is on the right of 0, and then here x is on the left of 0. So, and because these limits are not the same value, this is how we get that this does not exist. Because the limit from the left, we'll say, does not equal limit from the right. And I'll kind of specify what that means. But the point is that we can, as we, approach from two different sides, this goes to 0, this goes to 1, and having this gap right here, it doesn't matter how big that gap is, but that gap tells us the limit does not exist. So the fact that the left-hand limits and the right-hand limits do exist, then we can write that let's try to denote that. Let's try to specify, like, how can we write that in terms of notation, or how we did it earlier. So the left-hand limit we would write as the limit as x goes to 0, and like we would say, like, raised like a negative, I guess. I don't know how you would say what that looks like, but the way this reads is as x approaches 0 from the left. The negative means from the left. And we have limit as x goes to 0 plus, and then the plus means from the right, a limit of h of x is equal to 1. So basically I just said what we said in above into words. Well, into like actual notation. So again, x0 minus means to approach from the left. And whenever we say x goes to 0 plus, that means from the right. All right. And again, from the left just means you're approaching from numbers less than that, and from the right you mean numbers less than, greater than the limit. So now let's let's try to arbitrarize it, or generalize it. That way we can write it as as an arbitrary function with an arbitrary limit. So again, now let's try to put that into definitions. All right. So we write the limit as x goes to a from the left. Oops, not a to the negative 1. From the left of f of x is equal to L, to say the left limit of f of x as x approaches a from the left equals L. And that's how you would say that. You say, whenever you read this, you want to try to have this in your mind. Because, this right here specifies the direction you're coming from and which values you're approaching. And, the function obviously clarify, and the function, that the limit argument, as I would say, what we're actually taking a limit of. And then now what we're doing is just evaluating what the limit is doing, or what's the function doing as x approaches the limit from the left. All right, so as we have the left-hand version, we also have the right-hand version. And people say left-hand, right-hand, doesn't really matter, left, right, up to you. As long as it's clear, it's either the left or the right. So, and again, likewise we did with a similar one. Well, with the left one, we write the limit as x goes to a plus of f of x is equal to L, and it's kind of similar to what we just said, to say that the right limit of f of x as x approaches a from the right equals to L. All right, so basically it's just the same thing as above, but now we're just saying the different direction. So again, all these right here are just, kind of letters and stuff, kind of just specific arbitrary things at the moment. So let's actually do an example, like a concrete example to kind of investigate what we're talking about. So let's try to use a graph to determine some limits. So let's see. So what we're doing is we're going to find a graph of g of x. We're going to try to use that to determine if certain values or certain limits of g of x actually exist. So this will be x and y. And this will be like 1, 2, 3. And this will be like 1, 2, 3, 4, 5. So this will be all right. So what's going to happen is, oh my gosh, I hate this freaking iPad. All right. So we're going to 2, at 2, 3, we're going to have a hole. At 3, we're going to have, it's going to be right here, but it's also going to be right here. All right. So what's going to happen is we start from 0, the function is going to be at 0, and it's going to go to 2. And then from 2, it's going to go to 3. And then it's going to jump from this hole right here all the way back down. And well, not all the way back down, but, just to go off to do whatever it wants to do now. And this will be g of x. So as you can kind of see is that, this limit right here exists. There's not like a gap between them. I mean, my bad. But there's a hole here, but there's a gap here. And that's kind of a big difference right here. Is that this hole, there's actually not really a gap between any numbers there. But this right here, this part here does actually have a gap. Like this will be at 1, this is at 2. It's kind of an important distinction to know whether or not limits exist. So the first limit we're going to try to calculate is the limit as x goes to 2 of g of x. So again, as we approach 2 from the left, we get that this function approaches 3. And again, if we approach from the right, then if we just follow the function, then it also approaches 3. So in this case, the limit of g of x as x goes to 2 is 3. And this will be like our first section. And then our second one will be like, well, what happens if, now let's do the limit as x goes to 3 minus of g of x. And we want to investigate that limit. So again, the minus, 3 minus means from the left. So now instead of now we're going to approach 3 from the left. So we're going to follow this function all the way down. And as we see as, x goes to 3, f of x, hopefully that's clear, that goes to 1. So what we get is the limit as x goes to 3 from the left of g of x is equal to 1. And now that obviously kind of leads to another natural example. Looks like I'm just mixing up all the colors. What happens is, say, the limit as x goes to 3 from the right of g of x. So now we're going to be approaching it from the right. So now from values of x greater than 3. So then we're going to follow down the function up here on the right, and that approaches 2. So this limit right here is equal to 2. And then the last thing we're going to do is the limit as x goes to 3 of g of x. So in this case, the way we can evaluate this limit is by looking at the left and right limits. So here we got the left limit, is equal to 3. Well, not 3, but the left limit is equal to 1. And here we got the right limit is equal to 2. But these things are not equal. In the cases that they're not equal, like I said earlier, this means that this implies a graph, not a graph, but a gap in the function, like in the graph or whatever. That implies this limit right here does not exist. And the reason for that is, again, we say at the left, I'm not going to write it out fully, but the left and the right limits disagree. Oh yeah, okay. I forgot to give you guys the definition. All right. So what this kind of means is, and this will be very important whenever you do other kind of limits, especially when you do other problems. So as a result of, doing this kind of problem, and from the definitions we have is the limit as x goes to a of f of x is equal to L. We say if and only if the limit as x goes to a of f of x on the left is equal to L, and the limit as x goes to a from the right of f of x is equal to L. So in this case, what they mean is that this limit exists if and only if these two limits exist and are equal to the same value. If they're not equal to the same value, then you don't get, then this limit actually does not exist. That's kind of what we did above. Is that here we had a case where both of these were equal, which will be when we approach 2, we both get the same value of 3. And that's how we could say the limit as x goes to 2 or actually does exist. But on the case that, both of these are not the same value, then the limit of just f of x as x goes to a does not exist. That's kind of basically what we just did right here. And I really be tripping up my fucking words today. All right. So now we have, the last thing we need to do is kind of discuss infinite limits. So, we can approach certain values, and again, we specified above that the values we need to approach don't need to be in the domain. We don't have to be defined there. So when we choose this function like f of x, why can't we choose something with a vertical asymptote right there? And that kind of gives us the idea of infinite limits. I'm going to use green just to cross it out. All right, so now we talk about infinite limits. So what we're going to say is, I'm just going to write it down, that way it's kind of clear what's going on. Well, not clear, but to be technical, what's going on is we say sometimes functions will grow unbounded as you approach a certain value of x. Oops, we should say this. Approach a certain value a, certain values of x. Wait, what am I talking about? All right, sorry guys, I'm stupid. I literally just wrote something wrong. All right. So, okay. So sometimes the function grows unbounded as we, yeah, okay. Yes. Yeah, okay. Sorry, guys. Yeah, so sometimes the function grows unbounded as we approach a certain value of x. So again, what I've been just saying is just word salad at the moment because I can't say things properly. But, ignore that. But I can do the math. So I can show you what I mean. So an example of what I mean is, let's take a function that we all know and well, or at least I like to think about. Just some quick examples. Take the graph of 1 over x squared. All right, so just in case you guys aren't aware, what this function is going to be doing as x approaches 0 is going to go to positive infinity. And of course, again, these are the x and y axes. And then as we approach, 0 from the right, this function also goes to positive infinity. So what we say here, in this case, say the limit as x goes to 0 of 1 over x squared is equal to infinity. And again, kind of with notation as what we said earlier, we say like 1 over x squared goes to infinity as x goes to 0. Or another way of saying that in terms of, because earlier what we said was we can make f of x sufficiently close to something as x depending on x. What we're going to say here is 1 over x squared increases without bound as x goes to 0. And again, increases out without bound is just a fancy way of saying it goes to infinity. All right. So in this case, the limit of the function is actually equal to an infinite number. Well, not infinite number, but an infinite value. And this is the same thing. It could equal to negative infinity as well. But now let's do something with, like where the left-hand limits and the right-hand limits do not necessarily agree. So again, let's just look at a function that we all know and hope we'll all know and love. This will be 1 over x. So in this case, if we approach from the left, we have negative x values, so it's going to be negative. And as we approach, very small x values, this is going to grow unbounded. So this is going to be hitting off to negative infinity. And now if we approach from the right, where all the x values are positive, as we go to very small values of x, we're going to start dividing by a smaller number, which is going to take us to infinity. All right. So in this case, we kind of see its limits are not the same. So in this case, we say the limit as x goes to 0 from the left of 1 over x is equal to negative infinity, and the limit as x goes to the right of 1 over x is equal to positive infinity. And again, what this means is decreases without, what the negative infinity means says decreases without bounds. It's not bounds, it's just without bound. And the same thing for an infinity, just means increases without bound. And again, just in case, kind of like what we did in last case, or the last problem, is that the left-hand limits and the right-hand limits don't agree. I freaking hate this iPad. We actually get the limit as x goes to 0 of 1 over x does not exist. So you can exist if the left and the right limits both equal to the same value of infinity. It's either positive or negative infinity, but say if one is a positive version and one's a negative version, the limit does not exist. So one of the things we should note in this case is that, as you guys would tell me, is that x would be a vertical asymptote. Well, x equals 0 is a vertical asymptote. So let me just kind of clarify. You note that there's a vertical asymptote for those functions above. And the fact that, x equals 0 is a vertical asymptote for these, functions is actually kind of important. It's actually where the idea of asymptotes actually come from. Is that, your function is actually approaching an equation in this case, or approaches positive or negative infinity. So let's write that out formally. So formally, we'll say the line x equals to a is a vertical asymptote of the curve and again, we're just saying y equals f of x because, it could be a function of y, well, it could be y equals f of x, or just could be an arbitrary function. It doesn't matter how you want to write it, as long as you're clear of what you're saying. But we say a function has a vertical asymptote if at least one of the following is true. What the heck? All right. Sorry about all the issues. Okay. So now let's talk about the cases where vertical asymptotes exist. And again, this kind of comes from like what we're looking right here. You say the limit. This right here is the vertical asymptote because as limit as x approaches 0 is equal to infinity. And in these cases right here, we say that x is still vertical asymptote. Well, x equals 0 is still a vertical asymptote, even though one approaches negative infinity or positive infinity. So basically what we're doing is saying one of these situations has to exist. Something has to approach infinity. So again, there's 6 possible cases that can happen. So this will be blue or red. So here are the 6 possible cases. So we have the limit as x goes to a of f of x is equal to infinity. Limit as x goes to a of f of x is equal to negative infinity. And then we have to do the same thing from the left. Of f of x equal to positive infinity. Limit as x goes to a from the right of f of x is equal to positive infinity. Or we could now do the negative versions. So the limit as x approaches from the left of f of x could equal to negative infinity, or the limit as x approaches a from the right of f of x is equal to negative infinity as well. So again, this is a lot of conditions to kind of remember, but the main idea is something has to approach infinity, or something has to grow without bound as we approach the limit. And that's all we're really saying, is that in each of these examples here, something just went to infinity. It could have been positive, could have been negative, and because of that, a vertical asymptote exists. So now let's actually do an example. Again, because, examples are pretty concrete versus me just saying f is arbitrary and a is arbitrary. All right. So you want to evaluate 2 limits. So the first one will be the limit as x goes to 4 from the left of 3x over x minus 4. And the second one will be the limit as x goes to 4 from the right of 3x over x minus 4. As you guys can kind of see, if we plug in 4, we divide by 0, so we'd expect to see it's a vertical asymptote. All right, now let me try to draw the graph. So this will be x, this will be y, say 1, 2, 3. And I don't know if you guys know this, or maybe not be clear, maybe you plot it out, but there's horizontal asymptote at 3. We do 1, 2, 3, 4, and then there's a vertical asymptote at 4. All right. So if we approach from values that are less than 4, this the function is going to be negative because we're plugging in 3.9, and this part right here will be negative. And then as we approach 4, we're still approaching values from the left of 4, and we're going to be dividing by a small, you're going to be dividing by a small number that gets much, much smaller. And that means that function, as we divide by it, is going to go to infinity. Or as we divide by smaller numbers, it's going to go to infinity. And kind of likewise from the right. So we approach it from the right, now we're going to have numbers greater than 4, so the denominator will be positive. And then, so it's going to be 4.01, 4.001, and we're going to keep on dividing by numbers that get really small. So again, what that means is we're going to be going to positive infinity in this case. So let me kind of write that down, that way it's still not just more word salad. So you say the limit. Okay, no, let me rewrite that. Let me start with the reasons. So when x approaches 4 from the left, the numerator will actually be approaching a nice value. Because, well, in this case, it's approaching 12, because if you just, plug in, like, 3.99, 3.999, and you just multiply that by 3, eventually you'll get something that just goes to 12. And it's kind of easy to see. Eventually, you're just going to get, like, just 4 times 12 up top. But the thing is it's like the denominator is really, it's going to be kind of telling us what's happening. It's really going to be determining the behavior. So the denominator will be approaching a small negative value. And because of that, what happens when we divide by a small negative value, we get 3x over x minus 4 approaches a large negative value. So what this means is that the limit as x goes to 4 from the left of 3x over x minus 4 is equal to negative infinity. And the fact is that, and the reason for that is because this right here is negative, 12 right here is positive, so we're doing a positive divided by a negative, which is equal to negative, and then we're dividing by a very small number, and as we keep on dividing by smaller and smaller numbers, this number will become larger and larger and more negative. So that's why we have this limit to be equaling negative infinity, because we're dividing by smaller numbers and the fact that we're dividing by something that's negative. And if it's not a bit clear why it's negative, so again, so quick examples of what we're working with. Remember, the numbers here will be like 3.9. So this will be like 3.9 minus 4, which is equal to negative 0.1. X is equal to 3.999. So 3.99 minus 4 is equal to negative 0.01. And the fact is that all these numbers we're approaching are always going to be less than 4, so x minus 4 is always going to be negative. And the fact that we're approaching from left to right, and the fact that these numbers are going to be either going to be greater than 4 or less than 4, kind of determines the sign. So, and then let's do for the last part, for part 2. So, in this case, let's do for the limit as x approaches 4 from the right of 3x over x minus 4. Let's kind of try to determine what that is equal to, but I think you guys will suspect it's equal to infinity. So the numerator still approaches 12. And then the denominator, well, it's going to be basically doing the same thing as above, but in this case, instead of being negative, it's going to be positive. So let me write that down. Again, so the denominator will be approaching a very small positive value because this time we're dividing by, we're letting x be equal, 4.01, which is equals to 4.0001. And then whenever you do, x minus 4, we get, 0.01, 0.001, and these numbers get smaller and smaller, but they're still positive. So that's how you get positive, and that's how you get very small. And because that's happening, and the fact that 12 is also positive, so we're doing a positive divided by a positive, we get the quotient, or in this case, the function. So the limit of it, let's see, as x goes to 4 plus is equal to infinity. All right, so let me just rehash that since I'm tripping over words again. All right, so the fact is that the numerator is still approaching the same value. If we approach, 4.01 times 3, 4.0001 times 3, eventually that's just going to be 4 times 3, which is just 12. And again, likewise, as we did in the similar problem, so this right here is going to be positive. And now this right here is going to be small and positive, so this will also be positive. So it's positive divided by positive, which is equal to positive. And the fact that this thing is very small is going to make the quotient grow unbounded, or it's going to go to positive infinity. And that's kind of what we see as the graph, on the actual graph. We're approaching from values of x that are greater than 4, and then as we approach it, we're actually dividing by smaller and smaller positive numbers. So that's going to go to positive infinity. And again, if we approach them to the left, we're approaching by values that are negative, or not negative, but less than 4, so the denominator will be negative, dividing by the top, which is just a positive number. And as we approach it, it's going to go to negative infinity. And that's basically what we just affirmed in terms of words. And again, what this means is that the limit is x goes to 4 of 3x over x minus 4. So this part is done. This is just, a bit more to kind of notice. If the limit is x goes to 4 of 3x over x minus 4, that actually does not exist because we get positive negative infinity. And note that this also shows that x equals 4 is a vertical asymptote. And we could have said that it was a vertical asymptote based off either part 1 or part 2. So sorry about slurring my words a bit today, guys. But hopefully all this makes sense to you. It's kind of weird at first, but the idea that you have to keep in mind is what values are you approaching? What are you doing as you get closer and closer to certain values? And this whole idea of what happens when we approach is basically the idea of limits. What would happen if I just got really, really close to something? Where would I end up being? But hopefully this stuff makes sense. And remember, if you have any questions, feel free to just let me know.